Okay, we're going to kick it up a notch now. Much of the information is going to stay the same. For instance, I have not moved the meter stick. We still have a connection over here at the 75 centimeter point, and we still have a connection over here at the 5 centimeter point. But these tensions are going to change because I'm going to start off, not only do I have to hold the stick up 1.4 newtons, but I've substantially increased the load which has to be held up by placing a 4.9 Newton mass at 10 centimeters. So, well, geez, Heckman, this seems to be getting much more complicated. But, not really. All we have to do what we've already done. Imagine we're going to cut one of these strings. A better color, maybe. So that, when I cut this string, basically makes the other upward tension a center of rotation. Okay? And when it makes it a center of rotation, it turns both of these forces into forces that cause this thing to rotate in this direction, or clockwise torques. Whoops. So, how do we calculate the clockwise torque? Well, remember that all of our clockwise torques have to sum up to be equal to our torques in the counterclockwise direction. And in our case, it's this mystery scale over here, and we don't know what it reads currently. So I only have one counterclockwise torque, so it will be the only one. But they do all have to add up to cancel out because we're in rotational static equilibrium. So what I'm going to do is I'm just going to start off by saying I know the torque is equal to force times radius, where radius is the distance from center of rotation. So I'm going to take the force, the perpendicular force, of 4.9 newtons. Since it is at a distance of 5 centimeters, I'm going to take it times 0.05 newtons. So it's not creating a very large torque because it's not very far from the center of rotation. But we're going to add to it the 1.4 newtons, which is way out here at 50, which is a total distance, since this is at 5 centimeters, of 0.45 meters from the center of rotation. This whole kit and caboodle has got to be equal to the tension here, which we'll say is in cable 2. We'll call this one tension in cable 1. So tension in cable 2 times the distance from center rotation. Now this is at 75 and this is still at 5, so that makes it a 0.7 meter radius. So what I have to do is calculate, well, that color didn't work very well. Calculate this entire side over here, and then I need to divide it by the 0.7. So let's get after the business of doing that. So if we take 4.9 times 0.05, the number gets very small, 0.245 pretty quickly here. So that's a 0.245 newton meter torque plus the 1.4 times 0.45 gives us a value of 0.63 newton meters. I'm going to combine those together, and I get a value of 0.875 newton meters in the clockwise direction, which is being canceled out by torque 2 over here. So I'm going to take T2, well, it's funky T, excuse me. Oh no, this is actual T. What's my problem? That's not torque, it's a tension. Times, confusing, huh? 0.7 meters. So I divide through by the 0.7 meters, and I will be solving for T2. So my 0.875 divided by 0.7, and that tells me, it predicts that the force that this thing reads, if I erase that little black circle, will be 1.25 newtons. Let's see. Boom. Well, it's certainly right there in that neighborhood. Well, let's figure out what has to be on the other side. I know that the sum of these two forces has to be totally canceled out by all the upward forces, because these are down, and the tensions are up. So if 1.4 plus 4.9 is like 6.3, that's a 6.3 Newton downward force. Actually, a better way to write this, I think, is something like this. Let me get this rotational business out of the way. And let's put in the static business. We know that tension 1 plus tension 2 has to be equal to the downward forces added together. Okay, I'm back. I had a bit of an interruption there. Anyway, so we know that the downward forces have to add up to the upward forces, because it's also in translational static equilibrium. And since we know T2 is 1.25 newtons, and we know the sum of those two is 6.3, all I have to do is subtract out the 1.25. So, and I get a value for T1 of 5.05 newtons. That means it's going to, so we're predicting it's going to be right over here, somewhere. So that when I erase this thing, we'll see an arrow pointing to my little red mark. Boom. And look at that. Awesome. Here you go. I have left the stick in the same place. Let's mark these places in case you don't remember. This is 5 centimeters. This is at the center of mass, 50 centimeters. And this right here was at 75 centimeters. And now I have placed at a distance from the end of the meter stick, 80 centimeters from the end, I have placed a weight of 4.9 newtons. And I've covered up the scales. Right now, I want you to push pause and determine what the scales say. Once you think you have an answer, push play, and we'll go ahead and find the answer. Okay, here we go. Let's see if you got this right. And the unveiling. The first one is, boom, slightly over 6 newtons. And, well, I guess that's probably T2. And then over here, the T1. Whoa, just barely above 0 newtons. If you did not get that, you should go back and figure out what you did wrong. But moving forward to the next question. This is going to be a challenge question for tomorrow, or maybe, or the next day, likely. What I want you to do is look at this scenario. I'm going to set up a meter stick vertically between 2 ring stands. And on the meter stick, I'm going to attach a string at 35 centimeters, another string at 50 centimeters. I'm going to have those strings pulling in opposite directions, which are going to cause opposite direction torques. Now, here's the interesting thing. I want this thing to be in static equilibrium and translational equilibrium. So to do this, you probably understand that you'll need to hang a third mass. And we want to hang a third mass somewhere down on the other side of the 50 centimeters to balance this thing out perfectly. What I want you to do is I want you to determine the mass of this mystery mass and at what place, in other words, what centimeter mark on the stick do we need to place this in order to make the stick hover in both translational and rotational equilibrium. Please do this on a separate sheet of paper and have it prepared for Friday. It is a homework assignment. So that's weird. Normally we do those online.